Okay, so give the expected products of E2 elimination for each reaction. Using models would make this much easier because then you can keep track of the geometry a lot easier. Okay, so if this is an E2 reaction, then that means that we are making a what? We're eliminating something and we're making a double bond, right? In the E2 reactions, you're going to have some sort of strong base, right? You look at that, hey, that's a strong base. That's going to have a negative oxygen there, okay? This negative oxygen is going to take one of those hydrogens, an acidic hydrogen, right? And this acidic hydrogen is then going to give its electrons into a bond with something. So we have two choices, here or here. I won't specify which one yet, because you'll have to figure it out. All right. And those electrons are going to form a double bond, right? And then this other carbon will then have too many bonds on it. And so what does it do? Well, it has its leaving group, Br, leave. And that's why it's called elimination, because we eliminated the Br, right? And we left it with a double bond. Okay. So there's only one of these should be made. So which one should be made? Which one's more likely to get attacked? Which hydrogen is more likely to leave?
Would be the one next to the Br.
This one? How's it going to make a double bond? So think about that. If that one left, you'd put a double bond here, and then what leaves?
Yeah.
These aren't good leaving groups, right?
Because of the hydrogen.
Well, you put a double bond there, and I mean, they're not going to leave, are they?
Does that have to do with which one's in front? Like which hydrogen leaving? Because they're both on the
Yep, it has to do with the geometry and the location with regards to, yeah, these both have methyl groups.
Yeah.
So that's the only
Yeah.
thing that applies here. But for completeness, let me go ahead.
Oh, sorry.
No, you were ahead of that, which is good, but I just want to be complete. For completeness, the presence of a methyl group would stabilize a carbocation, right? And so the presence of methyl groups would help to make one site more stable than the other. But in this case, you're exactly right. There's methyls on both of them. And so the geometry is the only important factor. Or another way of saying that is Br is up towards us. One of these is on the opposite side of Br. The other hydrogen is on the same side, right? Okay. So which one do you think is more likely? You got two options and two people, so. You're going same side?
Yeah.
You're going opposite side or same side?
No, I just said the hydrogen is coming up as.
Coming up at you? So that's same side. Okay. It is opposite side. So what charge is Br? It's negative, isn't it? Okay, and so this is also negative, isn't it? So if it approaches this one to put the negative charge into a bond with it, it has two negative charge approaching each other, don't they?
Yeah.
If it approaches the other side, it approaches a positive charge. Yep. Okay. Or another way of thinking about that is the Br will slightly crowd this. Another way of thinking about that would be your orbital overlaps, which the positive side is on the same side as the hydrogen on the opposite side, right? The negative side, where the electrons already are, is on this side with this hydrogen. Okay? Those are sort of alternative ways to think. but they all sort of give you the same thing.
So in this case, do you not put the stereochemistry of like the atomic
Do you have a stereo center anymore when you have a double bond?
No.
No, you don't, do you? Yeah. So, yes, this actually becomes planar. Yeah. The double bond forces this into a planar configuration. So that doesn't have an up or down anymore. This one still does because this is still a stereo center, right? Okay.
Like when you're looking at these, how do you rank the acidity of like certain ones, you know? 'Cause like that was on midterm and I flipped last time.
Oh, okay. What do you mean by write the I'll have to.
Rank these, like which one's more acidic, you know what I'm talking
Oh, okay. Ranking acidity.
about?
So, whenever you look at these, the ranking of the acidities should always be in terms of how well they would stabilize once the proton leaves. So, how well can it hold on to that negative charge? Okay? So, for example, if this proton leaves, this would put a negative charge next to something that was already negative. And so that wouldn't be very stable, would it? But on the other hand, this is pulling electron density from that carbon and that carbon, right? And so if that proton would leave, that would leave you with a negative charge next to something positive. That positive carbon right there, right? And so, well, that seems pretty stable, doesn't it? Okay? Resonance structure would help as well. If you have a resonance structure, the negative charge can get shared, right? Things like, I'm going to use a really obvious example, but like carboxylic acid, right? Whereas the double bonded oxygen next to the single bond oxygen can share that negative charge between the two. Okay.
So if it can't hold on and it leaves, that's not acidic?
If it can hold a negative charge well, that would mean it's more acidic.
Okay.
Because when a proton leaves, an acidic proton, right, it has to hold on to a negative charge. If that energy is too high, the proton's going to come right back on, or otherwise known as doesn't leave. Okay? Does that make a bit more sense? Okay. The opposite's also true. Remember that acid and bases are two sides, right? So the stronger the acid, the weaker the base, right? Or another way of saying that is the stronger the acid, the more stable the base. So for example, HBr is a strong acid because bromide is extremely stable with a negative charge. Okay? And vice versa. An unstable base, high energy base, means a very weak acid, right? Okay. Did you guys want any more of these, or? Okay. Oops. All right, so let's draw the molecule on the canvas, blah, blah, blah. This one has two products that are possible. Again, these are all sort of the same things, right? Give the expected products of an E2 elimination. So you're always going to have some sort of double bond. In this case right here, it says two products. So you're expected to go ahead and draw out two of them, right? Okay? So your E2s, what do you always make what? Double bonds. And it's always going to involve one side of the double bond being where a leaving group is, right? What's your leaving group? Br, right? Because it has to leave with that negative charge. That's the stable negative charge, right? Okay. That's what helps make these acidic. Okay. Okay. So what are our choices for these hydrogens? It's never the hydrogen on the carbon, right? Can't be that. Because you couldn't move the dang negative charge anywhere and be stable, right? So it has to be the hydrogens that are, next to it, right? Otherwise, what we would refer to as like that alpha spot, right? The next one over. Okay, so this could be these hydrogens, or it could be this one, right? Those would both be options. So what do you think the most likely products will be? You have essentially three options, right? But do you?
What do you mean by three options? Like where the double bond would be? Like it's on
You have two options where the double bond could be, and then you have another one that would be, do you get rid of these, which of these hydrogens do you get rid of?
okay.
And many people would be concerned about which of those hydrogens you get rid of, but does it actually make any difference? No. No, you're gonna destroy your stereocenter anyways, aren't you? Yeah. The hydrogen's gonna be flat. There's no real difference, is there? No. So you have two things you need to write out, right? Two products. You have two options. And so those are your two products, right? So yeah, you write one with the double bond over here. Don't forget, you always need to get rid of the HBr. So the H on the left side, the Br in the middle. Like so. And you're just left with that H right here, where the Br used to be. See that okay? And then you do it for the other side, right? So we leave the left side out, same as it was, the reactant. Now we put the double bond on the right side instead. And again, the hydrogens end up flat anyways, so you don't actually have to put anything for the geometry of the hydrogen. Did you have any questions or anything you're having trouble understanding?
Why would you put the stereochemistry of the hydrogens on the top? Not.
This one?
Yeah.
Because, well, honestly, it doesn't actually make any difference. Yeah, it's a copy of this. And frankly, you would typically want to go ahead and just copy whatever the reactant is, because this is a computer, and computers are dumb. But you are absolutely right. The geometry here, because it's just hydrogens, there's no deuterium, there's nothing else, there is no actual stereocenter there. It's not chiral. Yeah. It really actually doesn't matter at all. Okay. Did anybody have any other questions right now? If nobody does, I'll go ahead and hit the stop recording.